This diagram shows what happens when we combine frequencies. If we pair the two smallest values first, we cause the smallest possible increase in the total weighted path length of the tree. This specific choice, made at every single step, ensures the resulting code is optimal. To find those specific values, a standard first-in, first-out queue doesn't work. We need a structure where the lowest number bypasses the line and jumps straight to the front based on its priority. We achieve this using a priority queue, implemented as a min heap. In this structure, the numerical value of every parent node is strictly less than the values of its children. Because of that downward cascading rule, the absolute smallest frequency in your entire dataset is permanently sitting at the top, immediately available for extraction. Since the Huffman algorithm requires us to locate the two smallest frequencies over and over again, the min heap acts as the mechanical engine for the entire construction process. This diagram shows our starting state. We begin by counting the frequency of every character and creating independent leaf nodes for each one. All of these disconnected nodes are then fed into the min heap, automatically sorting themselves into a hierarchy based on their frequency values. Now we start the loop. The two absolute smallest frequencies are extracted from the heap. These two leaves merge to form a brand new internal node. This internal node stores their combined mathematical sum, but it never contains character data. You must not forget this next step. This newly created internal node has to be reinserted back into the heap so it can be compared against the remaining elements in the next pass. Extract the two smallest, combine them, reinsert the sum. The priority queue dynamically resorts itself to accommodate the new frequency, and the rhythm repeats. This diagram shows the algorithm in motion. It repeats the cycle, hunting for the next two smallest nodes to pull, regardless of whether they are original leaves or newly created internal sums. Let's check your progress. Pause the video here and look closely at the final three nodes remaining in the heap. Identify exactly which two nodes will merge next. Then calculate what the final total frequency of the root node will be. The heap identifies the lowest values and pulls the last remaining elements, merging them to form the absolute peak of the tree. We stop when there is exactly one tree left inside the priority queue. At that point, the algorithm terminates and the Huffman tree is complete. This diagram shows how we extract our binary data. We apply a consistent rule to the branches. Every left-facing edge receives a 0, and every right-facing edge receives a 1. To map the codes, we start at the root and trace an unbroken path directly down to each leaf, recording the digits as we pass them. The resulting table shows the efficiency of the build. The highest frequency character ended up closest to the root, securing a compact 1-bit code, while the rarest characters were pushed to the bottom. By utilizing a variable length prefix code based on frequency, the system ensures that a character appearing thousands of times occupies a fraction of the space required by fixed bit formats. This image illustrates the algorithm's constraints. Because every node insertion and extraction from the heap requires a logarithmic operation, the time complexity is O of n log n, while the tree itself occupies an O of n space footprint. This diagram shows a memory trick for your exams. Remember the sequence FMCIRTC. Count the frequency, build the min heap, combine the smallest, insert the sum, repeat the process, finalize the tree, and generate the codes. Common exam mistakes include choosing the largest frequencies first, or accidentally building a max heap where the biggest numbers sit at the top. Either error leads to a non-optimal tree. Huffman coding follows the greedy method by making the locally optimal choice at every step and never reversing a previous decision. In Part 10, we will apply this entire process to a full numerical exam problem.